is very smaller element which is going to transmit power, and this is also a joining element. Pulleys are mounted on shaft, gears are mounted on shaft by means of this very small element which is known as key. As shaft is rotating with some torque, keys also are transmitting same torque, transmitting same power to that particular pulley. And for that sake, it is necessary for us to design keys also. So key is again a transmission element, though it is small element which is mounted. We know that there are different kind of keys used in engineering practice, but as a design engineer, we will be focusing on how keys are classified, what material is used for key, along with their design. And for that sake, let us see that what are the different types of keys. So this particular slide is showing you different type of keys used for joining, or you can say mounting pulleys, sprocket, gears, all those transmission elements. So somebody want to join? Right. So how keys are classified? Keys are classified based upon their cross section. So it may be round key, round key. Are you observing? Some dowel is shown. So it is a round key having round cross section. It is having circular cross section. Key may have rectangular cross section, and that rectangular key is also known as flat key. The second diagram shows that rectangular, it is also known as flat key. So we will find that key is having some width, it is having some width, it is having some height, width, height, and some length. So whenever we want to design key, we want to determine width of a key, height of a key, height also known as thickness sometimes, like thickness of a key, along with the length of key. When it is round key, we will be finding diameter and length of a key. Flat key will be square key when width and thickness are same, is it? So depending upon cross section, key is also classified into square key. You are observing in this first diagram itself that it is a square key. So round key, rectangular key, and square key. Depending upon uniformity of cross section, it may be parallel key or taper key. Taper many a times is provided. So you know taper. So taper always is desired in case of key, so that it will be easy fitment with the transmission element. Whenever we want to mount any transmission element, it can be easily mounted. So parallel key is a key whose height, whose thickness is uniform thickness, no taper is provided. And taper key is such a key which is having some taper. So you might be knowing that taper of order of 1 in 100. 1 in 100 means in 100 mm length, 1 mm taper is provided. 1 as to 100 means in 100 mm length, 1 mm taper is provided. Means when thickness is 8 mm, at length of 100 mm, it will reduce by 1. Thickness is 8 mm. So at a distance of 100 mm, we will find that thickness will be 7 millimeter. So taper of 1 millimeter in 100 is provided. So this taper helps in mounting different transmission element on the shaft. So depending upon cross section, it may be parallel or taper key. In this diagram, you are observing few more keys like feather key. Feather key is there. Woodruff key, jib-headed key, along with taper key. So last one is a taper key. So you might be observing that here thickness is more, and as you go along the length, you find that thickness reduces. So taper is provided on that particular key. Yes. So depending upon how keys are fitted, keys are classified into feeder key. Feeder. Which key is feeder key? A key which is either screwed to the shaft is known as feeder key. So you are observing in this particular diagram a feeder key, and feeder key has provision to screw it on a shaft. So many a times you want firm fitment in between key and shaft, and that can be achieved by using this feeder key. To mount feeder key, a slot is required on a shaft. So you need to cut slot over the shaft so that key will be fitted. Along with, there should be holes inside that slot, so that by using screw it is possible to grab that particular key on a shaft. Another key which is famous one is known as sunk type of key, sunk key. So in this second diagram, a front view and side view, you are observing that some key is fitted. Are you observing some rectangle is seen? So this is the sunk key. Sunk key requires keyway. It requires slot similar to feeder key. Correct? So you need to provide slot inside the shaft, and this outer one is indicating some pulley or some coupling which is mounted on a shaft. So this inside circle represents shaft. Over the shaft, we are going to mount this coupling. How the coupling is mounted? By means of this key having flat cross section, is it? But you are observing that half portion of key is going inside the shaft and half portion is inside that coupling. See in side view also, you are finding that some keyway is provided. Keyway is provided here. Half thickness goes inside that keyway. So what will be the height of keyway? Half of the thickness height of that particular key, is it? And half key will be fitted inside the coupling. So for such a case, sunk is required. That means slot is required. So manufacturing cost will increase and key will be fitted firmly inside that particular slot. The third key do not require that special keyway, or screwing arrangement also is not required. This key is directly mounted as a saddle on horse, is it? So name comes from saddle. It is just saddle which will be provided over the shaft. So you are observing here again in the third diagram that two keys have been shown which are mounted on saddle. So this is a shaft, and the lower portion of key is made so as to match with the shaft, is it? So it is made cylindrical. Lower surface is made cylindrical. So hollow saddle key will be fitted over that, and you are going to mount coupling or gear, whatever that, over that saddle key. Now, if you find the contact, there is frictional contact in between that saddle key and that of the shaft, is it? So it is just saddle which is mounted on a shaft. So we find that it is not a positive drive. While mounting flat saddle key, shaft portion is flattened, and over that the flat saddle key is mounted. Again, only flattened, no sunk is provided, keyway is provided. So you can say it is loosely fitted. For high power transmission, saddle key is not effective. It may slip, saddle key may slip when power transmission is high. So for low power transmission, we can reduce manufacturing cost by using such a saddle key. And one more key is the woodruff key. Woodruff key is having a special cross section. So we know the woodruff key So this is the Woodruff key, which is having some thickness and it has this cylindrical portion, correct? Semi-cylindrical shape is provided. It has a like slot is provided. See, there should be slot inside the shaft. So what is benefit of Woodruff key? It auto adjusts. It auto adjusts. So Woodruff keys are preferred in some of the application. So here you are watching image of the Woodruff key. So Woodruff key, and for Woodruff key slot is provided, and it is well possible to remove Woodruff key. So if you can force it out from the slot provided. Depending upon the provision for removal of key, that key may be unheaded key. Unheaded, no head is provided. So here you are observing all keys above are not having any head, whereas headed key will be having some head, correct? So jib headed key, it may be known as jib headed key. To some keys, this cylindrical head is provided. It may be peg key or J type of key. So if this cylindrical key is provided with the withdrawal arrangement, removal arrangement, so it will look like J as seen in image here. So it may be peg key or the same when head is provided, you can call it as jib headed key. So key may have head or may not have head. Now, after learning these keys, we will be learning how we are going to design the key. So it may be sunk key, it may be saddle key, any kind of key. Why it is used? It is used for transmission of power. It is joining element in between any coupling, any gear, any sprocket, and that of the shaft. So it is indeed necessary for us to learn that how keys are designed, because you are observing that as compared to shaft, as compared to the coupling and other sprocket gears, this has very small cross section. So it has very small cross section. It is important because it is transmitting same power that shaft is transmitting. And seen in a diagram is a sunk key. May I call it as sunk? Yes, sunk is provided. You are observing that some keyway is provided. Keyway is provided in a shaft, and inside that key is fitted. So coupling is not shown here. Only shaft along with key is shown. So this key is placed in the keyway, and whenever shaft is rotating, it is transmitting power. Key will also rotate with the shaft, and it is going to transmit power from this particular shaft to the transmission element in which it is fitted. So it is transmitting power means torque. Is it? We know that P is equal to 2 pi nt. We mean that it is transmitting torque. And you know that what is torque? Torque is nothing but force into distance. Torque is force into distance. So some torque shaft is transmitting. So same torque this key is transmitting, and torque is nothing but force into distance, and we know that it is tangential force. So if I am going to derive the force, how I may write? Torque T is equal to that tangential force causing rotation. Is it? This is the tangential force which is causing rotation of the shaft along with the key. Is it? So Ft is the tangential force. What is the distance of the tangential force from center of the shaft, or say center of rotation? Correct. Torque is what? Force into distance. Which distance? Distance of that tangential force from center of rotation. So this distance equal to radius, and radius is d by 2, half of the diameter. Is it? So I may write torque is equal to Ft tangential force multiplied by d by 2. So from power, I may find torque when RPM is known, and from this torque, we will be finding Ft, which is the tangential force at the shaft. See, whatever tangential force acting at the shaft will be acting at the key having width W and having height H, say. So whenever I want to design key, we will be considering that Ft is the force acting on that particular key. What is the force? Force is Ft. Ft is the force acting. So this is the tangential force acting on key. So whenever we are going to decide failure of key, we will be considering this tangential force. So tangential force is not given. We are supposed to find that tangential force. From power, find torque. From torque, find tangential force. That is equal to twice torque upon diameter of the shaft. Is it? So Ft we know. Now this Ft causes failure, and seen in this diagram is failure of the key. See, half portion of a key is fitted inside the shaft, and the upper half portion of key is fitted inside coupling. Half portion inside the shaft and remaining half portion is inside the coupling. So when force Ft is trying to rotate the shaft, imagine that coupling is unable to move due to very heavy load. Upper part is unable to move. It is locked, say, and shaft is rotating. When shaft rotates and the coupling is unable to rotate, maybe due to inertia, maybe due to locking, what happens? The portion of key trapped in coupling is not rotating, and a portion inside shaft wants to rotate. So likewise failure will take place. How failure is shown? Key will get cut along the length. Correct. This is the side view shown. In front view, you can imagine that half portion will remain inside the shaft, and remaining half portion, upper portion, will remain inside the coupling. So key will get cut along the length, and that wavy line indicates failure. Likewise, failure due to tangential force is known as shear failure. So this is the shear failure. Is it? Force is not axial. So the failure is known as shear failure. So we are supposed to consider shear failure of this particular key. Right? So, we will be writing strength equation for shear stress. Shear stress is equal to force upon area. So tau is equal to, how much is the force causing failure? From power, we have calculated this tangential force Ft. So Ft is the tangential force which causes failure. So tau is equal to Ft upon area of key resisting shear. Is it? So can you estimate the area? Lengthwise it is cut. So you can imagine that this W, this is the W, it is rectangular area naturally. This is W multiplied by length. Is it? W multiplied by length, W into L. Is it? So it is rectangle, correct? So from this diagram you can imagine, that when failure takes place here, this is the area which is going to resist shear. So W multiplied by L is the area which is going to resist this shear. So equation becomes tau is equal to Ft upon W into L. Tau is equal to Ft upon W into L. What is Ft? How we can represent it in terms of torque? It is 2T upon D. We have seen. What is Ft? Ft is 2T upon D. Let us put here. So strength equation indicating shear failure of key becomes Tau is equal to 2T upon WLD. W is the width of key, L is the length of key, whereas small d is the diameter of that particular shaft. So the first mode of failure by which key fails is a shear failure. So this diagram is indicating shear failure of the key. One more failure is possible to this key. Excuse me. Hello. Hello. Right. So shear failure of key is indicated in this particular diagram. Another failure possible, again, you know that there are two elements in contact. Always remember that whenever there are two machine elements in contact, P is contact with shaft. One more mode of failure is possible, and that is crushing. Crushing. Crushing is localized compression. Crushing is localized compression. Same tangential force Ft causes crushing of key inside the slot of shaft. So this is the shaft and this is the slot provided. So now imagine how crushing takes place. Shaft is stationary. Shaft is stationary, and you are trying to force it. What happens? Key will be pushed. Is it? Shaft, stationary. We are imagining that it is a driven shaft and a very huge load is mounted on a shaft. It is unable to rotate. And on other hand, from another shaft, coupling has received power and coupling is trying to rotate the shaft. So what happens? This tangential force is pushing this key. Tangential force is pushing key against this key weight. Key is pushed against this key weight. So you will find that at this particular height, half of the key is fitted inside the shaft. So this h by 2 portion along the whole length, is it? So this force is not only acting at a point, but it is acting over whole length of the shaft. So this is h by 2 over the full length L, is it? So we will find the area which is going to resist this crushing, here it should be crushing, area resisting crushing is h by 2 multiplied by L, h by 2 multiplied by L. So crushing will happen. Crushing is nothing but localized compressive stress. So we have taken strength equation as sigma C is equal to Ft upon h by 2 multiplied by L. What is the area going to resist crushing? It is contact area in between key and that of the shaft. So this diagram indicates the contact area of height h by 2 multiplied by L. So in strength equation, sigma C is equal to Ft tangential force upon that cutting that particular key lengthwise. So resistive area will be width of a key multiplied by length, rectangular area. And in this case, it is crushing. So only that portion inside the shaft will undergo crushing. So h by 2 multiplied by L. So whenever we are designing the, we will be first of all finding the force which is causing the failure. And then we will be considering shear and crushing failure of the key like this. Now, one more thing we will be learning here, and the statement is square key has equal strength in crushing and shear. So yes, it is true that whenever we are using square key exhibit same strength in crushing and shear. How? So square key is one which has height equal to width. Is it? H will be W. H will be W. Same. Both will be same. So these are the two equations. Shear strength equation, tau is equal to Ft upon W into L. Shear occurs along the width and length. So W into L. So we have Ft as 2T upon D. So what will be the equation? Shear strength equation. Tau is equal to twice T upon WLD. I will be resolving this equation for T, rearranging the terms. And I will be finding T. T is equal to WLD tau upon 2. Tau is the design stress. Design shear stress. Is it? Similarly, I will be finding crushing strength of a key. Earlier we have seen that crushing strength is given by sigma c is equal to Ft upon half of the height h by 2 multiplied by L. And as I rearrange and put Ft as 2T upon D, what I get? T is equal to HLD sigma c upon 4. So I have these two equations. T is equal to WLD tau upon 2 and T is equal to HLD sigma c upon 4. Their left hand sides are same, T, T. So I will be equating those. So equating T in shear strength and T in crushing strength. What I get? L get cancelled, D get cancelled. Is it? 2 will get cancelled. Here remaining is 2. Is it? And what I will be doing? I will be now converting the design strength into the material strength. So we know that whenever I am supposed to find crushing strength is equal to sigma YT. Is it? Always material's tensile strength is known. So crushing strength is double, many a times taken as 1.5 times, but at least it is equal to yield tensile strength. So sigma c is equal to sigma yt, and how we take shear strength? Shear strength is taken as half of yield tensile strength. So tau is equal to sigma yt upon 2. Is it? So I will be replacing sigma c by sigma yt, which is the yield tensile strength of material. See, sigma c and tau has some relation. These are the design strengths. And how those strengths are devised? Those are derived from the yield tensile strength. So sigma c is taken as sigma yt and tau is taken as sigma yt by 2. For square key, h is equal to w. So I will be making both replacements. So WLD sigma c is replaced by sigma yt upon 4 as it is equal to again WLD sigma yt upon 2 and tau is sigma yt upon 2. So 2 multiplied by 2. So we will find that both left hand, right hand are same, which indicates that when key has square cross section, its shear strength and its crushing strength is same. Is it? So many a times it is asked, it is very simple to derive that crushing and shear strength of square key is same. Just find out shear failure, crushing failure, resolve equation for T, equate both shear and crushing strength, and put design stresses in terms of strength of material. Sigma c is equal to sigma yt, and tau is equal to half of sigma yt. And when key is square, its height is equal to width. So you will get that both sides are same, indicating that crushing strength is equal to shear strength of a square key. Square key, is it? So W width, H is the height, and length are the three different sizes of any key, right? So here we are in position to design this square key, right? Now, in this relation, maybe in case of crushing, H and L, two are unknown, and in case of shear also, W and L are unknown. There are two unknowns likewise, is it? So there are empirical relations by which height is selected and by which width is selected. So commonly width of key is taken as d by 6. How much width is taken? D, which is diameter, divided by 6. So that is the empirical relation. What is empirical relation? Width of a key is taken as 1/6 of diameter, or you can say d upon 6. Okay. I'm sorry, height of key is taken as d upon 6, height is taken as d upon 6, and width taken as d upon 4. Width is larger, it is taken as d upon 4, and height is taken as d upon 6. H is equal to d by 6, and W is equal to d by 4. When it is square key, what are the empirical relations? W equal to H equal to diameter divided by 4. Okay, so thus it is possible for us to design both keys. So we know that there are some ways to design the key, and key is one of the transmission element which is used in engineering applications. Now we will be moving ahead towards coupling, and we will be learning that how couplings are designed. Okay, a very simple coupling initially we will be learning. So we have learned design of shaft, we know how to design keys, and now we will be moving towards coupling. So couplings are going to couple two different shafts. Couplings are going to join two different shafts. In many applications, it is desired that in a pump set, I want to connect shaft of pump with the motor. I am purchasing motor separately and pump is manufactured separately. So when I want to motorize the pump, I want to join motor with pump. So permanent welding like cannot be done, is it? So permanent joining method, if it is used, dismantling will be the problem while servicing. How I can dismantle motor? I want to replace motor, and for that particular sake, joining is achieved by means of coupling. There are different kind of couplings used. So in case of turbine and generator, turbine is rotating and that turbine is going to rotate the generator. So turbine shaft is to be coupled with generator shaft. So this coupling is a joining element in between two shafts. You may say driver and driven shaft. Is it? There used to be coupling in our vehicles also. So IC engine is developing power at crankshaft, and that crankshaft power is to be delivered to the wheel. So it is via coupling, a joint they are used. So whenever we want to transmit power from one shaft to another shaft, coupling is necessary. So some examples which we have discussed are given in this slide. So coupling also is a transmission element. Naturally, so coupling is mounted on driver and driven shaft. Coupling rotates with driver shaft and it is sending drive to driven shaft. So we will be learning this transmission element which is coupling. How couplings are classified? This is the classification of coupling. Couplings may be rigid one, rigid coupling, and that rigid coupling may be a muff coupling, it may be forged coupling, or it may be flanged coupling. Not written here, but rigid couplings are muff, forged coupling, flange coupling, and one of the type of flange coupling, that is protected flange coupling. Flexible couplings also are used, and examples of that are bush pin type of coupling and universal joint, which we have learned earlier. So what is difference in between rigid and flexible coupling? We know that rigid coupling requires alignment in between two shafts, requires alignment, and shafts are unable to have any angular movement in between. So we want true alignment in between two shafts. Their axis should coincide in horizontal plane and vertical plane also. So whenever we are using muff coupling, whenever we are using forged coupling, whenever we are using flanged coupling or protected flange coupling, alignment in between two shafts is necessary, and it is not permitting any misalignment in between two shafts. Whereas flexible coupling allows some misalignment. Some misalignment is permitted. It means that there may be some angular rotation permitted or inaccuracy, angular inaccuracy is possible. So bush pin type coupling is such a coupling in which some angular misalignment is permitted. And in case of universal joint, we know that shaft is able to rotate because wheel is moving up and down depending upon road condition, whereas gearbox shaft is stationary. So propeller is continuously moving up and down with the rear axle. So that adjustment is necessary, which is affected by universal joint. Seen in this particular diagram is a rigid coupling and a very simpler type of coupling, that is muff coupling. This is the muff coupling. Muff coupling is also known as sleeve coupling, muff or sleeve coupling. See, there is one shaft, input shaft, it is said to be input shaft, or you can say driver shaft. This is the driver shaft having diameter D. It is coupled to another shaft, output shaft, by means of some coupling. Output shaft driven, so it is driver, it is driven. Both shafts are aligned, their axes are aligned, is it right? In side view, you can see the shaft is carrying some key here. Key is mounted. So rectangular key or say flat key is mounted. slot is provided. Are you looking here? Slot is provided on both the shafts. Slots are matching and driven inside is a key. So a jib headed key is used. This key is carrying a hollow cylindrical element. Yes, it is hollow cylindrical. So this section view indicates it is hollow element. Are you observing? Hollow element is there, having diameter equal to twice d plus 30. Is it outer diameter? And what will be the inside diameter? It is fitted on shaft. So inside diameter will be equal to diameter of shaft. So this element is a muff. Hollow cylinder is driven. Is it? So when I want to join driver shaft with driven shaft, what I will be doing? I will be aligning these two shafts. Before that, this sleeve will be moved on one of the shaft. Okay, so this will be moved on driver shaft, and then driven shaft is aligned, and then again half length portion is on input shaft, and ensure that half length portion is on output shaft, and the key is driven so as to achieve a firm joint. Now what happens whenever input shaft rotates with some power? A shaft rotates as it transmits power. Key also will be transmitting power, is it, to this sleeve or say muff. Half muff is mounted on input shaft and remaining half is mounted on output shaft. So whenever input shaft is rotating, as muff is keyed to the shaft, via key, power is transmitted to muff, and that muff is going to rotate the output shaft also. So drive is sent from input shaft to the key, to the muff, again via key to this output shaft. So any motor shaft may be coupled via muff coupling, sleeve coupling to the pump shaft. Like this is the arrangement. So you are observing that a single muff or sleeve is used, which is in hollow cylindrical shape. Inside diameter is equal to small d, diameter of shaft, and outer diameter is doubled plus clearance 30 millimeter is added. So this is the simplest type of coupling. And when you withdraw key, as key is removed, joint will be dismantled. So remove the key, move pump aside along with shaft, is it? And now you are able to move the sleeve, and there will be dismantling in between input and output shaft. So this is the muff coupling. We need to design this muff coupling. So we know shaft design, we know key design, and now we'll be designing muff or sleeve here. Is it? One by one. So here we are considering that muff is weightless and shaft weight is not causing any bending. So shaft is designed for purely torsional shear stress. We'll be considering pure torsional shear stress in case of the muff or sleeve. See how we are in position to design the shaft. So shaft is shown here. Shaft is rotating. As shaft is rotating, as it is transmitting power, we know that its failure will be due to torsional shear stress. So we can find that how much torsional shear stress is induced in a shaft by using torsional shear formula, which is tau is equal to PR divided by J. Tau is the torsional shear stress, P is the torque, whereas R is the distance of maximum stress plane from neutral axis, and J is the polar moment of inertia. J is polar moment of inertia. Torque we can find from power. Power is equal to 2 pi nt divided by 60. So we can get torque as 60P upon 2 pi N. Here power is in watt. In problems, power is given in kilowatt. So 10 raised to 3 will come into picture. Is it? So 60 into 10 raised to 3 P upon 2 pi N, whatever that may be. So how to find tau? We have done it earlier in design of shaft. Tau is equal to T multiplied by R is D by 2. See here, this is the center, and which is the maximum stress plane. In this diagram you can see is maximum torsional shear stress can be found at the surface. What is distance in between this surface and axis or say center? Equal to radius, that is D by 2. And what is polar moment of inertia? For solid section, pi by 32 d raised to 4. So tau is equal to 16T upon pi d cube. As you select material, from the selected material you are in position to find design shear stress or allowable shear stress. Allowable shear stress is equal to half yield tensile strength upon factor of safety. Is it right? So we are in position to find that particular stress also. So here we are in position to evaluate diameter of the shaft. So we are considering torsional shear failure of the shaft. Once we have determined the shaft diameter, we will be selecting nearer standard size available. And then we will be designing key, which is again a transmission element. So earlier we have designed the key. So key is mounted on shaft. As it is mounted inside the keyway of the shaft, we know that shear failure occurs. Is it? And for that sake, we will be finding that what is the force which is causing shear failure. So from power, I may find torque, and torque is equal to force into distance. So tangential force is equal to 2T upon small t. So this is the tangential force, and this tangential force causes shear failure. What is area resisting shear? Area resisting shear is width of a key multiplied by length of a key. Is it? The diagram is indicating shear failure of a key. So along the length, key will get cut due to this tangential force. So tau is equal to Ft upon WL. It is Ft upon WL. So tau is equal to twice T upon WLD, and here empirical relations are shown. So we may select one of the dimension, either W or L empirically. So W, width of a key, can be taken as D by 4. W is taken as D by 4. So you find length. Otherwise, what we can do, we can take length equal to thrice D, 3 times diameter in case of muff coupling, and we can find width. Okay, so we'll be putting one empirically, and we will be finding other dimension by using this relation. Another failure possible with this key is crushing. As key is placed inside the slot of the shaft, crushing occurs, localized compression occurs, and we know that as half key is fitted inside the shaft, this side of the key is subjected to crushing. So h by 2 multiplied by L is the area of key resisting shear, resisting crushing. Here should be crushing. So sigma C is equal to Ft upon h by 2 multiplied by L. H by 2 multiplied by L. So L is known, we have selected. W we have calculated. We can find H from this relation. Okay, so this indicates crushing failure of key. So two elements we have designed, and now we'll be learning that how mask is designed, but not two